how can something be both a wave and a particle at the same time? I mean, really think about that. It breaks all the rules of our everyday intuition, but this single, baffling idea sits right at the very heart of how the universe actually works.
All right, so here's how we're going to tackle this. First, we'll start in the world we all think we know, the classical world. Then, we're going to see where it all goes wrong in the quantum conflict. After that, we'll look at the radical idea of a universal wave, put that idea through the ultimate test, and finally, we'll have to confront what this all means for the true nature of reality itself.
Okay, let's start on solid ground. In our big, everyday world, the rules seem pretty simple. Things are what they look like, and there's a really clear line between two totally different categories of stuff.
On one hand, you've got particles. You know, like a baseball. It's a solid thing. It's here, not over there. You can point to it and say, there it is. But on the other hand, you've got waves. Think about a ripple in a pond. Where is it? Well, it's kind of spread out all over the place, right? It doesn't have one single location. So in our world, it's one or the other. It's a particle or it's a wave. Simple.
Yeah, well, it turns out it's not so simple. Because as soon as we started building tools that could probe the tiny, microscopic world, we found out that those common-sense rules don't just bend a little, they completely shatter.
The whole thing started with light. First, there was something called the photoelectric effect, which basically showed that light delivers its energy in little packets, which we now call photons. And here's the weird part. A photon's energy depended on its color, its frequency, not on how bright the light was. Then, Compton scattering showed that these photons could literally collide with electrons and bounce off, just like tiny billiard balls. The evidence was piling up. Light, the textbook example of a wave, was acting exactly like a stream of particles.
And that, of course, leads to a fantastic, almost perfectly symmetrical question. If something we were so sure was a wave could act like a particle, could a particle, like a tiny electron, do the reverse and act like a wave?
And amazingly, the answer was a huge, definite yes. The smoking gun came in 1927. In the Davison-Germer experiment, they fired electrons, particles, at a crystal, and they saw a diffraction pattern. And that pattern is the undeniable signature, the calling card of a wave. The particle was, without question, behaving like a wave.
So this complete mess needed a new idea, a new rulebook to make sense of it all. And it came from an unlikely source, a French prince named Louis de Broglie. De Broglie's logic was just so beautiful and simple. He looked at nature and basically said, nature loves symmetry. So he reasoned, if waves can have particle properties, then it only makes sense that particles should have wave properties. This wasn't just some weird fluke, it had to be a fundamental rule for everything.
And this is it. This is the master key. Lambda equals h over p. Just look at what this simple little equation does. It connects a wave property, wavelength, right over to a particle property, momentum. The implication here is absolutely staggering. It means everything has a wavelength. An electron, an atom, a baseball, you, me, everything.
So you might be asking, okay, then why don't I see a baseball act like a wave when I throw it? And that's a great question. It's because the baseball's momentum is huge, which makes its de Broglie wavelength incredibly, ridiculously tiny, way too small to ever notice. But for something like an electron, with its tiny, tiny momentum, its wavelength is actually big enough to be significant on the atomic scale. And that's where its wave nature can't be ignored.
So, all of this, it leads us to the single most famous, most mind-bending experiment in all of physics. The one that really just rips the lid off the weirdness of quantum reality.
The setup is so simple, it's beautiful. You have a source that fires electrons just one at a time. They travel towards a barrier that has two little slits cut into it. And on the far side, there's a screen that detects and records where each electron hits, one by one, letting a pattern build up over time.
Now, what do you expect to see? If electrons are just little particles, you should get two stripes on the screen, right? One lined up with each slit. But that is not what we see. Instead, we get this, an interference pattern. This stripe pattern is something that can only be made if a wave passes through both slits at the same time and then interferes with itself. Let that sink in for a second. Each electron, flying all by itself, somehow goes through both slits at once.
And right here is where it goes from strange to just completely baffling. Scientists thought, okay, let's try to peek. Let's put a tiny detector right at the slits to see which one the electron actually goes through. And the moment they did that, the instant they found out which path the electron took, the interference pattern completely disappeared. Poof, gone. And what was left? just the two simple bands we expected in the first place. The very act of looking changed the result.
This mind-boggling phenomenon has a name, the principle of complementarity. And it basically means that nature offers you a choice. You can set up your experiment to see the particle nature of a thing, to find out which path it took, or you can set it up to see the wave nature, the interference pattern. But you can never, ever see both at the same time. The question you ask of the universe literally determines the answer it's allowed to give you.
So what is an electron? Is it a wave? Is it a particle? The modern answer is, well, it's neither. Our language, our everyday concepts, they're just not built to describe this. The reality is something much, much deeper.
So what is this wave if it's not a physical ripple? Well, the modern view, thanks to physicist Max Born, is that it's a wave of probability. The wave itself isn't a thing. Instead, its height, its amplitude, at any given point, tells you the likelihood of finding the particle at that exact spot if you were to look for it. So the particle always lands in one place, like a particle, but its journey is governed by this invisible ghost-like wave of pure possibility.
And this wave nature, it also elegantly explains why energy in atoms is quantized, why it only comes in specific, discrete amounts. Just think about an electron's wave trapped inside an atom. It's like a guitar string. You can't make a guitar string vibrate in just any old pattern. It can only form specific standing waves, which give you specific musical notes. Well, it's the same for the electron. Its wave can only fit into the atom in specific patterns, and each one of those patterns corresponds to a very precise energy level. This is the fundamental reason atoms emit light at very specific colors, and it's the core principle behind modern tech like LEDs and quantum dot TVs.
So, let's just nail down two of the most common myths. First, objects don't switch back and forth from a wave to a particle, they actually have both natures at the same time. It's our experiment that forces one of those natures to be revealed. And second, the quantum wave isn't a physical ripple in something, like a wave in water. It's an abstract, mathematical wave of probability that tells the particle where it's most likely to be found.
In the end, our classical words just fail us. An electron isn't a little ball, and it's not a ripple. It's a quantum object, a fundamentally new type of thing that doesn't have a perfect analogy in our large-scale world. Wave and particle are just the two masks it can wear for us, depending on how we choose to look at it.
And that leaves us with this really profound and maybe a little unsettling conclusion. The reality we observe isn't just some fixed thing that's out there. The very nature of what we measure depends on how we choose to measure it. The universe doesn't have just one story to tell us. Its answer depends entirely on our question. And that leaves us with the biggest mystery of all. What is reality really doing when we're not looking?